In this video, we will be describing Gibbs free energy, which is the amount of energy that we can usefully get out of a reaction. It also will enable us to determine whether a reaction will be spontaneous or non-spontaneous. In our previous video, we introduced the second law of thermodynamics, which stated that the entropy of the universe always increases. We can express this mathematically as the change in the entropy has to be greater than or equal to 0 for a process to occur. Now, we can take this concept of the second law of thermodynamics and use it to predict whether or not a reaction will occur. We can take our entropy of the universe and break it up into two components. The change in the entropy of the universe is equal to the change in entropy of the surroundings plus the change in entropy of our system. Right? So if we can monitor how our particular reaction vessel is changing, that's the change in entropy of the system, the thing that we're looking at. The surroundings, however, is a little bit more difficult. So one of the things that Gibbs did was he took our equation here, multiplied it by temperature, and the reason for multiplying it by temperature is, if you remember from our discussion on entropy, entropy is the dispersal of energy. And the amount of entropy that is induced, or the change in entropy, is dependent on the amount of thermal energy transferred divided by the temperature at which it is being transferred. So this concept of temperature is important when we're talking about entropy. So we take everything, multiply it by temperature. That gives us the temperature times the change in entropy of the universe is equal to temperature times the change in entropy of the surroundings plus the temperature times the change in entropy of the system. Now, the surroundings themselves are very difficult to monitor the change in entropy of, right? The surroundings are essentially anything that is not in the beaker that we're working with in the entire universe. That is very difficult to make any sort of a reasonable measurement of. However, from our previous discussion of entropy, right, the change in entropy is based on the amount of thermal energy transferred, the amount of heat transferred at a particular temperature. So if we can monitor the amount of heat that is transferred to the surroundings, we can infer the amount of entropy that comes from that heat. So if we look at just our temperature times the change in entropy of the surroundings, focus in on that, we can write that out as temperature times Q of the surroundings, right, over T. The Q of the surroundings over T is our change in entropy. It's the amount of heat being transferred to the surroundings divided by the temperature at which it's being transferred. And remember again that entropy can be thought of as the dispersal of heat. So we can take our temperatures, cross them out, and so we now have the temperature times the change in entropy of the surroundings is equal to the heat that the surroundings took in. This from our first law of thermodynamics, which says that the energy can neither be created nor destroyed. The energy from the surroundings had to come from somewhere, and it comes from the system. Because the directionality flow is the opposite. If energy flows into the surroundings, it came out of the system. We need to put a negative sign in front of the Q of the system. What this does for us is it gives us a way of looking at the entropy of the surroundings based on something in the system. Measuring things coming in and out of our beaker or our container is fairly easy to do, and so we can actually infer the change in the entropy of the surroundings by monitoring the energy flow in and out of our system. We can take this, plug it back into our equation here, and get temperature times the change in entropy of the universe is equal to minus Q of the system plus T times delta S of the system. Now, if we're working at constant pressure, so at the change in pressure equals 0. So if there's no change in pressure, then our Q is equal to delta H, right? This comes from our original definition of the change in enthalpy is equal to the heat under conditions of constant pressure. So this is the definition of enthalpy. So we can, as long as we're working under conditions of constant pressure, we can replace our Q system with delta H system. This gives us temperature times the change in entropy of the universe is equal to minus delta H of the system plus T delta S of the system. So, because the change in entropy of the universe has to be greater than 0, right, by our second law of thermodynamics, if this process is spontaneous, the temperature value, we're working in Kelvin, that always has to be a positive number. So a positive number times a positive number has to be positive. So this process has to be greater than or equal to 0 for a spontaneous process. For a spontaneous process or reaction. Now what Gibbs did was he took this particular value here and wrote it as T delta S of the universe is equal to negative delta G. Right, so the negative delta G is equal to the change in entropy of the universe. They are the same value, they're just opposite in sign. So if we try to re-express our equation here in terms of the Gibbs free energy, what we would end up doing is needing to multiply everything by -1, right, because of the opposite in sign. So I could do delta G is equal to the negative of the T times delta S universe, which would be the same thing as I have in the blue box, except times -1. And so essentially that's just flipping the sign. So the delta G for our system is equal to the delta H for the system plus T delta S of the system. Now, because we changed the sign, we end up flipping our greater than or equal to sign, right? So if before it had to be a positive number, because we took and multiplied everything by -1, it now has to be a negative number. So for a Gibbs free energy value, it has to be less than or equal to 0. And again, the reason why that happens is because the difference between our Gibbs and our entropy of the universe is this negative sign, right? Because there's a negative sign there. Anything that, for a spontaneous process, the term on the left has to be positive, but the Gibbs energy, the delta G part, here would have to be negative, because negative times negative gives you the positive. Okay, so for the Gibbs free energy, it has to be, the value has to be less than or equal to 0 for our spontaneous process. Okay, so this here, this Gibbs free energy equation with our greater than, our less than or equal to sign is going to be something that we will continually come back to figure out if a process is going to be spontaneous. We can also use this equation to determine what the Gibbs free energy is. So the Gibbs free energy itself is the maximum amount of work energy that can be released to the surroundings by a system for a constant temperature and constant pressure reaction. So as long as we keep the temperature the same, and as long as we keep the pressure the same, we will be able to determine how much work energy we can get out of a particular process. So the Gibbs free energy is often called the chemical potential, because it's analogous to the storing of energy in a mechanical system. So this is the amount of energy that we can get out of a chemical reaction. You can think of a battery, right? A battery would be a good example of a method for storing chemical energy, which can then be released to do mechanical work. So because the delta S of the universe determines if a process will be spontaneous, the delta G, which it is equal to, also determines spontaneity. The change in entropy of the universe is positive when spontaneous, which means that the delta G will be negative because the relationship is the delta G of the system is equal to the negative delta T times the change in entropy of the surroundings. So a process will be spontaneous when delta G is negative. This will occur, delta G will be negative when both delta H is negative and delta S is positive. These are typically exothermic reactions where the products have more different ways of dispersing than the reactants. Another one is where delta H is negative and large and delta S is negative but small. So your delta H term is what really drives the reaction. We could also have delta H is positive but small and delta S is positive and large. So the change in entropy of the reaction is what's driving the process. Or having delta H be positive and delta S be positive, but the temperature be really, really high. Delta G will be positive when delta H is positive and delta S is negative. This is a reaction that will never be spontaneous. If you want a reaction like this to occur, you will have to couple it with something else to drive the process forward. An example of this would be photosynthesis, right? We know photosynthesis occurs, but in order for the process to go, it has to have some external source of energy, which are the photons of light, right? The chemical process is carbon dioxide plus water gets converted into sugars and starch. That process would have a negative change in entropy, right? You're going from gas molecules that are well spread out into sugars, which are much more compact and have a lot less entropy. And the sugars have more energy than the carbon dioxide. So the delta H would be a positive value, delta S would be negative. So the way that we can get carbon dioxide to react with water to form sugars is by giving it extra energy, and that energy comes from the photons of light that help drive the photosynthesis process. So another key aspect is that when the Gibbs free energy is equal to 0, the reaction will be at equilibrium. So more pictorially, what we had just said is that when our delta H is negative, delta S is positive, the reaction will be spontaneous at low temperature. It will be spontaneous at high temperature. An example would be 2 N2Os goes to form 2N2 plus O2. A way of sort of coming up with this table yourself is to look at the reaction and just look at what the signs are going to end up being. So if we take an example of the third one where they are both negative, right? If H is negative, if H is a negative value and S is a negative value, then what would make G negative? Well, we have sort of two conditions. We have either low temperature or high temperature. When I'm doing this myself, I like to use the extremes for temperature. So low temperature, I set it at 0, and high temperature, I make it infinity. So if we work with low temperature and T is 0, then 0 times anything is 0. So our Gibbs free energy, the delta G at T equals 0, 0 Kelvin, would be the same as our delta H system. So if delta H system is negative, delta G would be negative. If, however, we're working with temperature equal to infinity, right, temperature equal to infinity, then infinity times anything will dominate over the delta H system, right? So we would essentially be subtracting negative infinity, which is the same as adding infinity, Infinity is a very large positive number. It's infinite, in fact, and so that would make the delta G positive. So what we can say is that if both delta H and delta S are negative, the process will be spontaneous at low temperature, but it will be non-spontaneous at high temperature. We can do the same thing for our last example, where they're both positive, to look to see what happens. So if H is positive, delta H is positive, and delta S is also positive, at T equals 0, then the delta S part goes away, and so delta G would be equal to our delta H. Delta H is positive, therefore delta G is positive, so the reaction would be non-spontaneous. If we look at infinite temperature, so we would have a positive number minus infinity times a positive number, so that would be subtracting infinity. So whatever the positive value is, if you subtract infinity from it, you're going to get negative infinity, right? So our delta G would be a negative number at high temperature, and therefore it would be spontaneous. Okay, the last example that we hadn't covered yet is if H is positive and S is negative. So if H is positive, S is negative, at T equals 0, we have H minus 0, H is positive, so G will be positive, right? So the reaction will be non-spontaneous. If we go to T is equal to infinity, right, then it's a positive number minus negative infinity, because it's subtracting infinity times a negative number, so that would be negative infinity. Subtracting negative infinity gives you a positive infinity, and so G would be positive. And so the reaction would also be non-spontaneous at high temperature. Now, because there was the last two conditions where it changed spontaneity based on the temperature, there has to be a way of determining what temperature that change is going to occur. So we can use our equation and just solve for the temperature. So the place where it's going to occur is when we're at a state of equilibrium, right? So that would be, or we could also think about it where it changes sign is where your delta G is equal to 0, right? So where G goes from being a positive number to a negative number, or a negative number to a positive number, that occurs at wherever Gibbs free energy is equal to 0. So we have essentially 0 is equal to delta H minus T delta S. We're interested in the temperature at which this occurs, so we need to get temperature by itself. So we're going to move the H to the other side. So this is negative delta H is equal to negative T delta S. I'm going to divide both sides by negative delta S. The negatives will cancel each other out. And so I'd be left with the temperature is equal to delta H over delta S. And you'll note, if you look at the previous slide with the table that we had, this occurs when they both have the same sign, right? So the times in which you have a transition is if they're both either negative or they're both positive. And so if our delta H was a negative number and delta S was a negative, that would result in a negative over a negative, which would be a positive value, which works out because if we're working in Kelvin, our temperature has to be positive. Now, the thing to keep in mind for this particular thing is that our delta H values are typically in kilojoules per mole, and our S values are typically given in joules per mole Kelvin, right? So you have to make sure that you either convert your H to be in joules, so either convert your H to joules or convert your S to kilojoules, right? Because the units need to be able to cancel out. Okay, so this concept of spontaneity is, it's really, will the reaction occur without an outside force pushing it? So Any spontaneous process is irreversible because there is a net release of energy when the process proceeds in that direction. The spontaneous processes will only go in one particular direction. There is a driving force for the reaction to go in that particular direction, which means there is a force that is pushing against the reaction going in the reverse direction. So a reversible process will proceed back and forth between the two conditions. Any reversible process is at equilibrium. So if you're working with a system that's at equilibrium, you can give it a little shove in either direction and the reaction will proceed. This results in no change in free energy. So if a process is at equilibrium, there is no net driving force, and so there is no change in the free energy for the process. It just stays at equilibrium. If a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. So a couple examples that we can think about is, let's say you have a fancy showroom car and you put it in, leave it in a field for, a decade or two. It will eventually rust. So the rusting process is a spontaneous process. You don't need to put any external energy into it. It will occur. Now, spontaneity, or a spontaneous process, does not say how fast the process will occur. It just says that it will occur. For example, diamonds will spontaneously convert into graphite, but the process is very slow, on the order of geologic time slow. So you don't have to worry about diamonds turning into graphite in your lifetime. The process is very slow. So the car will rust, right? That's a spontaneous process. You can take a car that's sitting in a field, a rusted out vehicle, and convert it back into showroom fashion, but you have to put a lot of effort into doing so. And so you can drive non-spontaneous processes, but that's through a lot of energy being expended elsewhere, which would be, you removing the rust from the hood and, applying more paint and doing a lot of work to get it to go from the field wreck to something that would be on a showroom. Another example would be a frying of an egg, right? You can't unfry an egg. Once the reaction goes, the reverse direction is not possible. So spontaneity means that it is a process that will occur in the current conditions that you have set forth without any external outside energy.